Then let's do a very special other sequence. Maybe one like this. What if we have -1, 2, -3, 4, -5, 6, -7, on and on and on. How would you write the explicit form of this? Well, let's do this first, right? If we pretended these negatives weren't here, if we just kind of look at the absolute value of the sequence, what would the pattern be? One of the simplest patterns known to man. It would just be 1, 2, 3, 4, 5, 6, 7. And so in that case, AI would equal what? If we just had 1, 2, 3, 4, 5, 6, 7.
Would it just equal I?
Just equal I, yeah. We start at 1. So the question is, though, what do we kind of have to do to this sequence to get to this sequence? See, this sequence is, well, it's really, I mean, you could write it like this. You could write it as AI equals I if 2 divides I, and negative I, 2 does not divide I. Or you could write it piecewise like that if you remember piecewise functions. But that's very unsatisfying to me. A piecewise function where you don't need it feels like a failure. There's a really easy way we could write this. Well, so I guess what do we really want to do? We want to multiply this by something. And this something we want to equal, we want this to be -1 when I is even and 1 when I is odd. Because if we have that, then we're perfect. Then we're good. Because whenever I is even, wait, I'm sorry, other way around. We want it to be 1 when I is even and -1 when I is odd. Because then notice all the odds have negatives on it. And so if this thing we have multiplied by truly is -1 when I is odd, well, that works for that. And if it's 1 when I is even, well, that gives us 2, 4, 6, 8, just like the 1. So what can you think of that is -1 when I is even, or 1 when I is even and -1 when I is odd? Why not -1 raised to the I? Because then notice, -1 raised to the I when I is even, -1 squared, for example, is 1. -1 to the 4th is 1. -1 to the 6th is 1. -1 raised to an even is 1. And conversely, -1 raised to an odd is -1. This is a fact about -1. So if we write it out, we get A1 is -1 to the 1 times 1. -1 to the 1 is -1 is -1. A2 is negative 1 squared times 2, right? Just plug in this formula. Then we get negative 1 squared is 1 times 2, which is 2. A3 is negative 1 cubed times 3. Negative 1 cubed, negative 1 times negative 1 times negative 1. That's going to be negative 1. This is negative 3. A4 is going to be negative 1 to the 4th times 4, which is going to be 4. It goes on and on like that. And you notice we get exactly what we wanted to get. Does this make sense? Got a tentative nod from Herman, so we're gonna go with that. Yeah, totally. Yes, I think it makes sense. This totally makes sense, right? This is what negative 1 does. Negative 1 raised to a power, if you guys remember calculus and series and sequences from that, negative 1 raised to a power alternates. It goes negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1. And so that is exactly what we're taking advantage of. And this is exactly an alternating series. I'm sorry, not series, sequence. Alternating sequence. Alternating sequence, by definition, is a sequence that alternates from negative to positive in every consecutive term. So, for example, we could have one minus 4, 9, minus 16, 25, minus 36, 49. Right? Just alternates positive, negative, positive, negative, positive, negative, positive. And the way to find an explicit form, or formula, to find explicit formula, first find formula for the absolute value of the sequence. And then, here's the fun part, here's what makes it alternating. Multiply by negative 1 to the k, or negative 1 to the k plus 1, depending on how your sequence starts. And I'll write here, no shame in guess and check. Here's what I mean by this. So we'll end in a second. So 1, negative 4, 9, negative 16, 24, negative 36, 49. First consider the absolute value of the sequence. So get rid of the negatives. That's going to be 1, 4, 9, 16, 24, wait, this would be 25. There we go. 36, 49, on and on like that. And what's the explicit formula of this?
I squared?
Exactly, for I squared for all I greater than or equal to
1.
Exactly, starting at 1. Now,
I think I figured it out.
what's it going to be? Alpha wants to solve the puzzle.
-1 to the power I multiplication I square.
So this is close. And here's where the no shame in guessing check comes in, right? If this is our explicit formula for all I is greater than or equal to 1, right? Then what we get is we get the sequence, we start at 1. A1 is -1 to the 1 times 1 squared, which equals -1 to the 1 is -1.
Then my power is I plus 1.
Exactly. Yeah, exactly. That's all it is. You try it with with a -1 raised to the I. That doesn't work. Try with -1 raised to the I plus 1. Right? It's guessing check. And now this will work. It all depends on where it starts. So here we get A1 is -1 to the 1 plus 1 times I times 1 squared, which equals -1 to the 1 plus 1. That's -1 to the 2. -1 squared is 1 times 1 is 1. Then we get A2 is -1 to the 2 plus 1 times 2 squared. -1 to the 3 is -1 times 2 squared is 4, -4. A3 is -1 to the 3 plus 1 times 3 squared. -1 to the 4, -1 to an even is always going to be 1 times 3 squared is 9. And it goes on like that, on like that. The point is this successfully recreates our sequence. So we'll do more of that. Tomorrow. But the point is, this is the idea. First, do it with the absolute value, take away the negatives, and then either multiply by -1 to the I or -1 to the I plus 1. I put K here. The point is, the index doesn't have to be I. You could use K or J or M or whatever you want to use. But the point is, this is the idea. Any questions, anybody? Okay, then since for all people in the Zoom call, there are no questions, that means there's not exist anyone with a question. So I can successfully rest tonight. Then that is sequences. We'll do a little bit more with that tomorrow. And then we're on to induction. Gonna start proving some cool things. Not that we haven't already proven cool things. I feel like this class always ramps up. I mean, this is the nature of math, never being satisfied, always moving on. It doesn't matter that math exists for 2,000 years. You've already proven 1,000 incredible things, but there's more things to prove, more techniques to learn, more fields to open. Yeah, so it's fun. I like it.